Hello, today I would like to show you how to use Virtual NanoLab and the Atomistics toolkit to simulate lithium-ion diffusion in lithium iron phosphates. So we will use the notched elastic band calculations and harmonic transition state theory to estimate diffusion barriers and diffusion rates. So I use the crystallography open database plugin to find a lithium iron phosphate material. So I just search for it and locate it in the list and simply add it to the builder. In this particular case, I also swap the axes around a bit before I send the structure to the script generator in order to set up DFT calculations and geometry optimization using DFT. So I give the script a suitable file name for output like that. Set up the calculator to use polarized spin because we have iron in this structure, and I'd like to use the GGA method and set up a suitable k-point grid like this. For basis set and exchange correlation, I use the defaults. In the optimized geometry widget, I make sure to not constrain the lattice vectors and save the trajectory. Then I send the script to the job manager in order to execute it. Save the Python script first like that, and then execute the calculation. It takes roughly 30 minutes to run on a modern computer. Once it's done, the optimized geometry is transferred to the builder, and I copy it in order to create initial and final structures for two different NEB paths, path B and path C. So in path B, the lithium diffusion will be along the B direction in the unit cell, and in NEB path C, the diffusion will be along the C vector. So I need initial and final structures for both NEB paths. So the initial structure for B should contain a vacancy. So I simply remove this lithium atom right here, and then in the final configuration on the NEB, I want a lithium atom to diffuse into that vacancy. So I mark it gold in order to just use it for visual purposes, and then I drag this lithium atom onto it and fuse it. So that's diffusion from to there. And for the diffusion along C, again I need a vacancy right there, and the final structure, then in that structure I want a different lithium atom to diffuse into that vacancy. So again I use the gold trick just for visual purposes. Then I drag this lithium atom onto that vacancy right there in order to allow it to diffuse along C. So I now have initial and final structures, and all four of them needs to be geometry optimized before constructing the two NEB paths. And I do that in the exact same way as I optimized just before, except for the fact that I'm gonna use non-polarized simply to make the calculations faster, even though one really should use polarization for this system. But just for demonstration purposes, we're going to do it fast. And in the optimized geometry, I make sure that the lattice vectors are constrained and save the trajectory to NC like that. And then I simply run the calculation using the job manager. I do this for all four of the structures I just made. And like that. And once they're all done, the optimized initial and final structures can be dragged to the builder, and we can start setting up the notched elastic bands. So simply drag and drop initial and final states onto the widget here. Choose the image dependent pair potential method and adjust the maximum distance such that I get 9 NEB images. And then I compute the initial NEB path for direction B. It looks like this. Then for constructing the NEB for diffusion along C, I choose the initial and final structures, adjust the maximum distance to get 9 images again, and create that initial NEB path. And this is what it looks like that. Okay, so both NEBs are now sent to the script generator in order to optimize them using DFT. And I add the calculator and optimization. The calculator is set up exactly like just before, or at least it should be. I may not show it right here. And in the optimized geometry, I use the climbing image method and save trajectories to a specific NC file. There may be quite a lot of them actually, so it might be a good idea to save them to separate file. Again, execute the calculation using the job manager. Give the script a reasonable name like neb_b and execute the calculation. This may take several hours on a modern computer. But once the calculation is done both for NEB path B and C, the results are gonna pop up on the lab floor, and the second NEB item is the optimized one, and we can visualize it using the movie tool. This looks like that. For the NEB-C, the optimized path looks like this, and up here we have the transition state. Okay, so in order to compute diffusion rates, we use the analysis from file functionality and select the optimized NEB object, which is the second one. And then we use the HTST event analysis object and choose a fixed prefactor of 10 to the power of 13 and save the results to a separate NC file like that. We run that script using the job manager. Using the fixed prefactor makes the calculation extremely fast, should only take a few seconds. So just execute it like that, and the result is gonna pop up pretty soon. And doing the same for path C, we can compare the diffusion rates for the two different diffusion paths, which are right here. So using the HTST rates plugin over on the right hand side here, we see a forward and backward rate of roughly 2 to the power of 6 per second for diffusion along the B direction, whereas for diffusion along C, the forward and backwards rates are much smaller, which can also be seen in the Arrhenius plot. Thank you.